Hanji Pulwan ki halchal, welcome back to another video. So let's begin with the next lab. So in local search, like how do we determine the neighbors? So there are only 4 ways to determine the neighbors. That includes flip based, move based, swap based, and custom defined. So one of the flip based means like in the binary representation, we can just flip the single bytes with the neighbors and we can define the neighbors. So another thing is like move base, like we need to move the elements to the adjacent nodes and by which we can define the neighbors. Swap base means we can swap two of the elements with each other, and this is how we define neighbors. And the custom define, we need to define some rules and constraints, and as you know, on towards your left I have defined some rules and constraints to define the neighbors. So what is the difference between a random walk and a random restart? Random walk generally represents a random initial state and moves to the randomly chosen neighbors. And because of this, it is likely to get stuck in the local optima. Whereas on the other hand, we can see that the random restart performs many of the random walks in the local optimum to reach a random new initial state, which is basically which increases the chance to finding global optimum. So what are the two weaknesses of the stochastic local search? So first is getting stuck in the local optimum, then the second one is inefficiency. As I told, it gets trapped in the local optimum because there are suboptimal solutions and which are better than the neighboring solutions. And inefficiency for big problems, it requires like more iteration, more loops, so therefore it doesn't find it to be more efficient and get stuck. So other was the traffic flow, that was related to like there is 4-way stop for the school iteration, and like we can provide alternate routes. So this was the route. We have the school here. These represents the signs, and this provides a truck route, and here we can put the stop signs, and we usually provide the stop route from the outside to give traffic more, space to go. So here we need to require 4-way stops for the school intersections, obviously, and alternate routes for the trucks from the exterior, and consequent intersection should have the same light controls. That is basically the constraints that we need. It is like somewhat of that thing, like if it's a red light and that's the school, and roundabout should be at least one per block to have a good flow of traffic. And greedy descent search process includes selecting the variable with most conflicts and then assigning the value to the selected variable that minimizes the conflict. So I'll show you here like how many conflicts are there. I'll just show you. I think you can see like ample of conflicts, and this is somewhat correlated to the next question over here. And one more thing, this is the graph that shows the time constraints, time in milliseconds, and these are the successes. This is the runtime distribution. These are the steps that are counted till 100. Okay, so moving further, based on the greedy search, the variable that conflicts most is intersection 2. So see, it conflicts the most because both intersection 1 and 3 due to constraint, this one is C3 and this one is C2, just provide some constraint like true, false, and true to them. So to avoid this, we should assign a stop sign to the intersection 2, which could have consecutive uncontrolled sections. And last but not least, the question was like, is it possible to find 100-step solution for the random walks? No, because the complexity of the problems, like we saw so many conflicts inside them, so random walk get easily trapped in local optimum, and here you can see it is trapped in local optimum and still running. And if you see, even it's reaching more than 100 steps, right? And it's not sufficient to explore the vast search space. And I'll show something more here. If we go create and set some constraints over here, and if we choose custom, this is C1, this is C2, because we need false here, and this is C3. So now I will solve this again with batch run, and batch run has ended. We can see the plots. This is the plot. See how the conflicts ended up to 5. And now I'll show the trace. Batch run again. And let's use another algorithm to solve it. Random walk was this one. Now we use greedy descent. Batch run ended, auto solve. See, it's again going over 100 steps. I'll stop this. I'll show the plot. See, this is the conflicts and the step count. No, the trace is not showing. Okay, so we'll move to another algorithm. That would be greedy descent with random walk. And now we'll again batch run it. Batch run ended. Let's see the plot. It's somewhat same like the previous one, but a little bit different. This was the runtime distribution that we get. Thank you.